Hi, I'm long, as in, I'm long. Okay, here's the deal. This is the Thermodynamics chapter for AP Chem for chapter 6. We're going to look at energy and thermodynamics. Okay, and with that, let's get started. So we have to look at what is thermodynamics. Well, the first thing about it is, it's the study of energy and all the changes that it undergoes. That is a very big thing in terms of studying science, because in chemistry we have thermodynamics, we have it here in physics, we also have it to an extent in biology as well when you're looking at changes of energy amongst living things as well. So what is energy exactly? Well, the first thing about it is the energy is the ability to do work, like some of you are trying to do right now with your notes. You're trying to actually do work because you want to fill this in. Okay? It is conserved because the first law of thermodynamics says energy is not created nor destroyed. It is in fact conserved. It does change form. It is made up of heat and work. To which we have to talk about what is a state function. Now you haven't heard that in Chem or H-Chem, but in AP Chem, the idea is this: a state function is telling us it's independent of the path, or how do you get from point A to point B. That's the thing about it. In physics, we talk about displacement and distance. Whereas distance is how long it takes you to get around to something, whereas displacement, we look from our starting point to our end point. And that's what it is here, okay? It doesn't matter, this is like a straight thing here in terms of pressure and volume from the initial, your start, to the final, okay? Whereas the state function going initial to final, it doesn't matter the path that it takes. It's a little bit weird, but I hope it'll make a little bit more sense as we get on here. So the state of function is independent of the path or how you get there. Okay? It's as long as you started at point A, you go to point B. It doesn't matter how long it takes you to get there. It doesn't matter how many paths you cross in order to get there. It just means I'm going from point A to point B. I'm starting from my start, my initial, and I go to my end, my final. It doesn't matter if I do it like this or I wait 150 years. That's what a state function is. Okay? So when we look at work, we have to look at it as force times distance. Physics, spoiler alert, work is in fact force times distance, and we use the term Newton to describe that, but we're not going to worry so much here. At the moment, because more often in AP Chem we're looking at joules, which is our unit of energy. So heat is energy transferred between objects because of the temperature difference. Think about this for a moment. Why is it when you were a little kid your mom told you not to touch the stove? Well, when the stove is hot and you touched it, okay, you had a bunch of energy transfer from the stove to you. Why? Because you're cooler than the stove is, and energy will rush from the hot object to the cold object. Fire Science 101, if you want to learn to be a firefighter. That's the first thing you go through. Okay? Let's keep going. So if we look at the universe, it is really divided into two halves. There is the system, and there are the surroundings. Well, we're going to deal in AP Chem with the system only. We're not going to worry about the surroundings. Well, wait, what do you mean by the system? Are you talking about the system that keeps us AP Chem students down? Is this the system that makes fun of some of us by Mr. Canu and not others? No, not that system. We're talking about, if I'm looking, a system is something that we can define. Okay, that we can say that it is a system if we're looking or we are examining something. For example here, okay, if I'm looking at a system and I'm interested in the pressure differences between sucking water through a straw, right, then do I care about what's over there at the back door? No, I don't. That's the surroundings. My memes are surroundings. My awesome UCLA beanie, Ross, it's surroundings. The system is what is here. The water in this cup, this, that is the system. Which, okay, that felt better. So that's the system. It's defined. All right? Now, we have to look at endothermic, exothermic reactions. Pretty key idea, because when we look at exothermic reactions, remember, we're talking about releasing energy into the surroundings. You might remember a lab that we did in chem or H-chem where we mixed vinegar and baking soda. And you noticed, you may remember that the temperature went down. Okay, well, what was happening? Well, energy was being absorbed from the liquid part of our solution while the vinegar reacted with the baking soda. Well, if energy is being absorbed, the temperature goes down, and that's what we call endothermic reaction, because it was absorbing energy from the surroundings, whereas exothermic, we're talking about it's giving off energy, kind of like those hand warmers that you guys use and your hands are cold at night and you're at the game and we're losing or we're winning, but your hands are cold and you want that exothermic reaction. Well, that releases energy. And the same thing, when we look at water here, we can talk about endothermic, exothermic as a process, because the whole idea is, where is the heat going? So if we're looking at going from ice to steam, okay, we have to add energy to it. That's an endothermic process, right? Because you have to add energy to it. When you drop ice into your cup of soda, we want our soda to be cold. Kind of like how I serve pop quizzes, okay? But the ice is absorbing the energy. It is an endothermic process. It's absorbing the energy from the soda. Now, exothermic, on the other hand, okay, if you pour charcoal lighter fluid on the barbecue, you take a match and you light the barbecue on fire. Notice I didn't say lit on fire, because some of you guys will go, that's funny, he said lit. Grow up. Grow up, man. So anyways, that's the difference between exothermic and endothermic. Now remember, if you're removing energy, going from steam to ice, that's an exothermic process, because you're taking heat out of the water and putting it in the surroundings. That's the bottom line. Now, how does that apply for chem? Okay, well, let's look at this one. Here we're going to burn methane and oxygen, and we're going to walk away with CO2, H2O, and heat. Okay, that is very much an exothermic reaction. How will I know that? Look at the heat. The heat's being generated. So here you see a graph, and right now we're just looking at potential energy. Here's CH4 plus 2O2. This is what we have here. This is our reactants. This is what we're starting with. Now, you may notice there's a bit of a hump here. And then you see it going down like a roller coaster at Magic Mountain. And then at the bottom here, we end again CO2 plus H2O. And then here we got a bunch of heat. What is up with this? This is looking at the process of an exothermic reaction. Okay? So we're starting out with CH4 plus 2O2. This is where we're at. We have all this energy that's available. Okay? Now this hump, well, what is that hump representing? That's the activation energy. That's the energy needed to get that reaction going. Because just putting methane and O2 in the same jar, it'll sit there and it will do absolutely nothing. Like some of you guys have been doing the past 10 minutes. Right? Right. It's on you. So that's activation energy. Okay? That activation energy gets the reaction going. Okay? Now the process is happening. We're getting all this heat being released, and the potential energy is going to drop down to here, down to pretty low. Okay? Now the question is, well, what's happening? Well, as this thing is going, as the heat is being released from the reaction, okay, we got potential energy that's going down. Well, hey, what's going on here? Well, remember, bonds are being made, bonds are being broken. And there's definitely an exchange of energy that's taking place. Now, let's look on the other side of the coin, okay, where we have N2 plus O2 and we get 2NO. Okay, again, we're dealing with this little hump there. Well, remember, we have to add energy into it in order to make it go, and then that final thing, that final hump, there, that final bit of energy we need to take N2 plus O2, and we get new. Okay? So the endothermic reactions are absorbing the energy from the surroundings. I don't know why that thing is there. Okay. Any questions at this point? You might want to pause the video here and stop and see if you got, just take a moment and take all this in. Don't worry, I'll be waiting. And we're back in action. Okay, let's keep going. So, direction. In other words, there's got to be a direction when we're talking about all this stuff that's happening. So every energy measurement is going to have three parts. There's going to be a unit, which could be joules or calories. It's not of, it's or. A number, how many? Okay? And a sign to tell which direction is it going in. Okay? A negative, it's exothermic. If it's positive, it's endothermic. That's a pretty important idea to understand. Okay, now I got to check the time here because I can't magically see what we got. I got some 12 minutes there. Okay, so I got some time. The camera runs out at a certain point. So let's go ahead. If we're looking at endothermic and exothermic, here's some pretty important ideas. If it's exothermic, it's negative. Okay, so if heat is being given out, okay, then it's exothermic and the direction is negative. You'll have a negative sign. On the other hand, if it's endothermic, it's going to be plus because it's absorbing and we're adding all this heat in. Okay? So with that, we have our system here, like I mentioned earlier about this being a system, and my awesome memes back there, that's part of the surroundings. Okay, my awesome UCLA cap. See that, Ross? Right there. Okay, that's all those times you wore the SC stuff there, buddy. Okay, so from the system, having the energy go to the surroundings. That's where delta E means our change in energy is less than 0. In other words, it's negative. Okay, negative. When we look at the other side of the coin, this is an endothermic happening here where energy is going into the system. Okay, so I use my thing again where energy is going into the system. I put this on a heater or stove, or I put it next to the sun, but it's absorbing the energy from the system outside, okay? And that's where delta E, that change in energy, is greater than 0. Yeah, absolutely. All right. Any questions on that? I can't answer them. All right. So here's some rules when we talk about for heat and work. Heat is given off is considered negative. If heat is absorbed, it's positive. The work done by the system on the surroundings is positive. The work done on the system by the surroundings is negative. This kind of sounds confusing, and I can understand that. Okay? So I ended up finding this. I found that this seems to work out a whole lot better, okay? Because this is a nice visual. The energy, so we look at the first law of thermodynamics. Remember, the whole point about thermodynamics is the energy that is moving around, okay? That's the idea. So the energy of the universe is constant. The law of conservation of energy. Now we got to define some terms here. Q is equal to heat. Okay? Q is equal to heat. So, if Q is a large number, it's hot. On the other hand, if Q is very small, it's not very warm now, is it? Right. Now, W is equal to work. Well, that's kind of an easy connection, W equaling work. We can go with that. So when we look at our change in energy, we've got to look at what the heat plus the work are. That's the thing, okay? And when we decide the signs, we have to look at it from the perspective of the system. And I think I am going to stop here and call this one for part 1. This is Long, signing off.